Okay, so let's get started. So far, we have defined two kinds of cohomology. Theorem cohomology and cohomology with compact support. Today, I'm going to define a new kind of cohomology with compact vertical support. And it is a cohomology theory for vector bundles. So I will first have to discuss vector bundles. So cohomology vector spaces give you diffeomorphism invariance. And they're useful for distinguishing diffeomorphism classes of manifolds. And cohomology with compact support, is useful for distinguishing among isomorphism classes of vector bundles. Okay. So let me first discuss vector bundles. A vector bundle is a kind of a fiber bundle, but the fibers are vector spaces. So you can think of it like this. So every fiber is a vector space, and like a fiber bundle, it's locally trivial. Okay? So every point has a neighborhood over which you have a product. Okay? So this is the definition. So you start with C infinity surjection. Whose fibers are vector spaces. Are vector spaces of dimension R. Okay. And then, so this is for all X in M. And then it is a vector bundle of rank R if it is locally trivial. So if there is an open cover U alpha of M and fiber preserving diffeomorphisms P alpha from pi inverse of U alpha. Okay? That's what we define to be the restriction of E to U alpha. Okay? And you have a diffeomorphism to a product. Okay? And this diffeomorphism has to be linear on each fiber that are linear isomorphisms on each fiber. Okay. Okay. So it is really just a fiber bundle, but the fibers are vector spaces. And then the diffeomorphism that gives you um, um, the open set, as a product has to be linear on each fiber. Okay, okay, because each fiber is a vector space. Okay, okay, so that's a vector bundle, and you already have a couple examples. I mean, the cylinder is a vector bundle over the circle. Okay? And the Möbius strip is also a vector bundle over the circle. Oh, yeah. So here, okay, this is the open Möbius strip. And the fibers are open intervals, but an open interval is diffeomorphic to R. So you can think of the fibers as R. Okay. And then this Möbius strip is also a vector bundle over a circle. Okay. Now, the cylinder is a product. It's S1 cross R. Okay. So that's a product bundle. And we can define morphisms of vector bundles. So what is a morphism of a vector bundle? That's called a bundle map. A bundle map from one vector bundle to another it is just a C infinity map that preserves the fiber, C infinity fiber preserving map. Okay. So in other words, it maps a fiber over X to another fiber over X. And what do you think another requirement is for a bundle map? It should be a C infinity fiber preserving map, and we're talking about vector bundles. So if you are talking about morphisms of fiber bundles, then the map just has to preserve the fiber. But for a vector bundle, what would be an additional natural condition? Yeah, it has to be linear on each fiber because each fiber is a vector space. So a bundle map from one vector bundle to another is a C infinity fiber preserving map that is linear on each fiber. Okay. And then if a bundle is isomorphic to a product, then we call it a trivial bundle. Okay. Yeah, once you have the concept of a morphism, then you have the concept of an isomorphism, right? It's a morphism that has an inverse. And then you can talk about a trivial bundle, a vector bundle is trivial if it is isomorphic to a product bundle. say M cross R to the R projecting to M. Okay. Oh, yeah. Okay. Now, yes. So in the definition of a vector bundle, these diffeomorphisms phi alpha are called trivializations. Okay, so yeah, so phi alpha is a trivialization. Yeah, it actually gives you coordinates on each fiber. Okay? And of course, you can have different trivializations on the same fiber, right? Because so you might have a vector bundle, and you have these trivializations that overlap. So, okay. So here's U alpha, and then here U beta, okay? And so in the intersection, then you have two trivializations. That's like having two coordinate systems on the fiber. So then you have transition functions, right? So like this gives you, so here you have a diffeomorphism to, U alpha, U beta cross R to the R. And then over here you have a diffeomorphism to U alpha cross R to the R. And if you are in the intersection, it's gonna be, yeah, the intersection here is diffeomorphic to a product here. And so let's call the intersection U alpha beta. Okay? So this intersection is diffeomorphic to U alpha beta cross R to the R. Okay? But it's also diffeomorphic to U alpha beta cross R to the R via phi beta. And so you can look at the map going from here to here. Okay, so that's phi alpha on this would be U alpha beta cross. Okay, no, just a minute. Yeah, so over the intersection U alpha beta. Okay, so you can look at phi beta inverse and then compose with phi alpha. That would go from U alpha beta plus R to the R to U alpha beta plus R to the R. Okay? So this is called the transition function for U alpha, U beta. And so you're going to start with a point here, say X, V. And then this is going to go to, well, it's fiber preserving, so X should go to X. Okay, now V should go to something via a linear transformation, And that linear transformation we call G alpha beta, and it depends on X. Okay? Yeah. So the transition function will have this form where G alpha beta assigns to each point in the intersection a linear transformation of R to the R. So that is GLRR, the general linear group. Okay? Yeah. Okay. So that is called a transition function. So for a vector bundle, you know, the transition functions, they always have values in the general linear group. But sometimes it can have values in a subgroup. So, for example, you know, like if you like can fix an, you know, orientation. Well, R to the R has, you know, a standard orientation, right? And it might happen that these G alpha betas, they always preserve the orientation. In that case, this linear transformation will have positive determinant. And then the transition function would have values in a subgroup of the general linear group, you know, GL plus, the subgroup with positive determinants, right? Yeah. So sometimes you can have transition functions with values in a subgroup. And that is called a reduction of the structure group, okay? So let H be a subgroup of GLRR, okay? If there exists, you know, a trivialization so a trivialization is given by an open cover, and then on each open cover you have this local trivialization phi alpha, okay? So if there exists a trivialization of the vector bundle E such that the transition functions, they all have values in H, then we say that the structure group can be reduced to H, okay? Then we say the structure group is, well, normally the structure, GLRR is the structure group for any vector bundle of rank R. But if you can use a subgroup instead, then we say that the structure group of E can be reduced to H, okay? So that is what is meant by the reduction of structure group. And so we define a vector bundle to be orientable if the structure group can be reduced to GL plus. A vector bundle is orientable if its structure group can be reduced to GL plus. So if you can reduce the structure group to GL plus, then there is a consistent way of putting an orientation on each fiber of the vector bundle, okay? Because like, okay, on an Euclidean space, you have an orientation. So each fiber here has an orientation. And then you just use this diffeomorphism, okay, to carry the orientation over here. Now, normally when you do that, there's a problem of consistency because there's also an orientation using this trivialization phi alpha. And so you will get an orientation on the fiber also from this one, phi alpha, and they may not agree. However, you know, if the structure group have positive determinant, then the orientation on the fiber has to agree, right? Because if they disagree, then when you take the composition, you know, you'll have the opposite orientation, and that means the determinant will be -1, okay? Yeah, yeah. So when you have an orientable bundle, it's possible to give an orientation to each fiber of the vector bundle. And, you know, there are two ways to do it because you can say, okay, the orientation of the fiber here will be the same as the orientation here. And that will be consistent, right? Or you can say, well, whenever you have a trivialization, the orientation on the fiber will be the opposite of this orientation. Okay, and that will give you a different orientation on the fibers of the vector bundle. So you have a choice, okay? So what we're gonna do is like, we're gonna say that the vector bundle is oriented, you know, if the fibers of the vector bundles are given the orientation through the trivialization, okay? So like if you fix a trivialization and then, yeah, then this will have the same orientation, you know, as R to the R, yeah. Yeah, okay. So you can have a different orientation, different trivialization where, you know, this goes to the opposite orientation, right? So, so in order to fix an orientation on the vector bundle, you have to fix a trivialization, okay? Yeah. So, okay. Yeah. Okay, now you can have trivializations where, the transition functions sometimes have positive, sometimes have negative determinants. So we don't want that. So we're going to say that a trivialization for a vector bundle E is oriented if all its transition functions have a positive determinant. And then an oriented vector bundle is a vector bundle with an oriented trivialization. Right? Yeah. So it's a pair. You have the vector bundle and you have an oriented trivialization. And that oriented trivialization will tell you how to orient the fibers of the vector bundle. Okay. So earlier, when we talked about cohomology with compact support, we introduced integration along the fiber, right, in order to calculate the cohomology of Rn. Now, to integrate along the fiber, you don't need that the form has compact support on the top, because all you need is that, the form should have compact support along each fiber. Okay? Then you can integrate. Well, you also need that each fiber is oriented. Yeah, so we're going to define a new kind of form. It's called a form with compact vertical support. Forms with compact vertical support. Okay, so let's say you have a vector bundle. And it's oriented so that each fiber is an oriented vector space, well, Rn. Now, you might say that, okay, a natural candidate for a form with compact vertical support is that it should have compact support on each fiber. Okay, so a candidate for such a form by such a form, I mean a form with compact vertical support is, say, a form on the top such that the support of omega restricted to each fiber is compact, right, in the fiber. Now, the problem with that is that if you integrate a form like this along the fiber, the form that you get may not be continuous. Okay? And so it would certainly not be C infinity. Okay? And in the homework, I wrote down an example and I asked you to check that when you integrate that form, which has compact support along each fiber, the form that you get downstairs is not continuous. Okay? So this definition does not work. Right? With this definition, integration along the fiber may result in a non-continuous form. Integration along the fiber of a C infinity form may not be C infinity. And so we need to use a different definition. So in order to have, to check C infinity, you need like values in the neighborhood, okay? And it turns out that a definition that would work is that, so every point, so whenever you take a compact neighborhood, whenever you take a compact set here, and you look at its inverse image, the support of omega intersected with this should be compact. Okay? So this will imply compact support along each fiber, because if you take a single point here, which is compact, the inverse image, is a fiber, and then it says the support of omega intersected with the fiber should be compact. Okay, so this is the definition of a form with compact vertical support. Now, in the first printing of the book, we actually used the wrong definition. We used this one, and then somebody sent us an email, with this counter example that now I put in the exercise in homework 3. And so, well, at the time, I didn't want to make a second edition. And so I just corrected it in the next printing. Yeah. So when you get the book, you have to look at the printing. It has to be the third printing. The third printing has everything corrected. Yeah. The first printing, is from 1982. It's in a lot of libraries. And it has the wrong definition. Yeah. Uh-huh. But the book that I gave you, yeah, is from 1995, and everything is corrected there. Okay. Okay, so let's write down the correct definition of a form with compact vertical support. Mhm. So, um, so omega in um, a smooth form omega on the total space E of the vector bundle has compact vertical support if for every compact set K in M, the support of omega intersected with pi inverse of K is compact. And that will guarantee that when you integrate along the fiber, you'll get a C infinity form. Okay? All right, so we have defined now this forms with compact vertical support. And this is the notation. You just put compact vertical, okay, as a subscript. C infinity forms, K forms on E with compact vertical support. Okay. Now, you can check that the exterior derivative will take a form with compact vertical support to a form with compact vertical support. And that this, forms an algebra. No, yeah. Well, right now we don't care about the product structure, but yeah, but it certainly forms a vector space, and so you can define cohomology. Okay, so this complex of forms with compact vertical support with the exterior derivative is a differential complex and then its cohomology is the cohomology with compact vertical support. So we define the cohomology of E with compact vertical support to be, the cohomology of this differential complex. Okay, yeah. Okay, so that gives us a new kind of cohomology. And well, now we want to compute this cohomology, so for example, we should first compute it, say, for a product bundle. And so to compute it, we're going to define integration along the fiber. Okay. Yeah, so let me give you the theorem. This theorem is called the Poincare lemma. with compact vertical support. And it calculates the cohomology with compact vertical support of the product bundle. And it says that this is the same as the cohomology of M, but, you know, it's just like for cohomology with compact support, okay, yeah, you have to decrease the degree by R. Okay? So this is the Poincare lemma. And the way we get this isomorphism is by integrating along the fiber, R to the R. Okay. So let's define integration along the fiber. So I want to define a map that goes from K forms with compact support on E to K minus R forms on M, okay, by integrating over the fiber. And so let's first do it for a product where M is just a coordinate chart. Okay, so let's now assume M is a chart and then E is just the product. Well, so again, you know, on this product, you have coordinates, all right? You have coordinates T1 to TR with coordinates T1 to TR on R to the R. Okay? Yeah, so this product is really just a subset of an Euclidean space where you have coordinates x1 to xn and t1 to tr. Right? And then again, there are two types of forms. Type 1 and type 2. So forms on E are sums of two types of forms. Okay, when we defined type 1 and type 2 forms before, we just had U cross R, right? And what are type 1 forms back then on U cross R? This was, yeah. Right, yeah. It has only, you know, the space coordinates. It doesn't have dt in it. Okay? And type 2 forms have a dt in it. Okay, now now we have T1 to TR. So what should the type 1 form be? You see, the thing is, we want to integrate out the DTs, okay? So, and then like type 2 will give you something non-zero when you integrate with respect to T. Okay? So a type 2 form should have what? What in it, so that when you integrate with respect to the T's, you can get something that's not zero. Yeah, you need D1, DT1 to DTR. So a type 2 form has DT1 to DTR in it, all of them. Okay? So a type 1 form is one in which you don't have the whole set of DTs in it. Okay? So a type 1 form looks like this, f of xt, okay? I'll just say, okay, dti, that means it's dti1 wedge dot 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 dti something, okay? But where the cardinality of I is less than R. Okay? So you don't have the whole set of dt1 to dtr. Okay, so that's a type 1 2 form, a type 1 form. And the type 2 form, you know, has all of them in it. Okay. And then integration along the fiber on type 1 would just be 0 because you don't have enough DTs in it. And then for a type 2 form, you just integrate over Rn the function with respect to all the T's. Oh, R to the R, right? That's the fiber. And you have dx j left. Yeah. So that's integration along the fiber. All right. And so let me see. Yeah. Okay, let's take a break for 10 minutes. Okay, and we'll continue with this. Okay, so we have defined the integration along the fiber. And I feel that there are two things I really should prove, you know. And the first is that when you start with the C infinity form, that means F is C infinity, after you integrate, you should get a C infinity form, right? With our definition of vertical compact support, okay? So that's the first thing I should prove. And then I should also show like where this assumption of orientability of the vector bundle comes in, okay? And that comes in proving that this definition actually is independent of the coordinate system so that you can globalize it, you know. Okay, so first let's show that when we integrate along the fiber, we get a C infinity form, okay? So yeah, so if say omega is f xt dt 1 to dtr, which dxi is C infinity, then pi star of omega is C infinity. Okay. So this is C infinity on M. And here is C infinity on U cross R to the R. Yeah, so pi star of omega is the integral over Rn of f of xt, okay, dt1, dtn, dxj, and let's call this function, this is just a function of x, g of x. So we have to show that g of x is C infinity with respect to x, and we can do that by showing that the partial derivatives exist. So let's take the partial derivative with respect to, say, xj. Okay, so if we know that f is C infinity, so if we can bring the partial derivative inside the integral sign, then you'll be integrating a C infinity function, and so, the result will be C infinity. So the whole question is whether you can differentiate under the integral sign. And here is where you use the compactness of the support. Let me see. Okay. Now, I was told not to go below that, and then let me see if it works this way. Doesn't really work, right? Because I can't write that high. All right. Well, it's okay. Temporarily, you just can't see that if you're online. Okay. So, or maybe, okay, maybe what I can do is I can write over here. Yeah. Okay, so what do we know? Yeah, so to check whether something is C infinity, you only need to check it at the point P. And so you take a compact neighborhood of P. And then we know that the support of F intersected with pi inverse K is compact, right? So, you fix a point P in U and a compact neighborhood K of P. A compact neighborhood just means a compact set that contains the neighborhood. And then we know that support of F intersected with pi inverse of K is compact. Okay, so that's by hypothesis. So it's compact. And pi inverse k here, it's just k cross r to the r. Right? We have the trivial bundle. And, you know, this neighborhood, you can choose it to be a coordinate neighborhood. That means, you know, it's diffeomorphic to some open set of a Euclidean space. Okay, so then this product is diffeomorphic to some open set of a Euclidean space. And if you have a compact set in a Euclidean space, it's closed and bounded. So it's bounded. So it is actually contained in some rectangle, right? K cross the product of AIBI. And since the support in here is contained in this, when you integrate, yes, when you integrate, instead of going from minus infinity to infinity, you can just go from AI to BI, okay? So thus, the integral over Rn of f of xt dt1 to dtr, that is actually the same as the integral from, say, A1 to B1 f of xt dt1, okay? And then you know, it just integrate over closed intervals, okay? Now, in this situation, there's a theorem from real analysis. You know, when your domain is a closed rectangle, your function is, I think it's only needs to be continuously differentiable up to some certain order, but we have C infinity, so certainly we can apply the theorem. Yeah, in this situation, when you have a closed rectangle as your domain, you can bring the derivative inside the integral sign. So this is equal to ddxj f of xt. Okay. Yeah. So this is by a theorem from real analysis. And therefore, this function, this is what we call the xj g of x. Yeah. So you can keep differentiating, you know, by bringing the derivative under the integral sign, and therefore g of x is C infinity. Okay. Hence, uh, and so high lower star will go from C infinity K forms with compact support to C infinity K minus R forms on U. Not E, but U cross R to the R. Okay? Yeah. So we use the compactness hypothesis here. Okay? And then the next theorem is that the definition of pi lower star is independent of coordinates. So if you have two coordinate systems, then you have two definitions. Let me, is it still here? No, the definition is gone. All right. So now, yeah, so let's say U x1 to xn be a chart, and then you have T1 to PR. So this is, say, on U cross R to the R. So that's a chart of E. And then V cross R to the R, Y1 to YN, U1 to UR, okay, be another chart. And now you can, type 1 in one chart will be type 1 in any other chart because the T's transform, you know, by themselves, and you can't change the number of DTs, right? So you only need to worry about type 2, okay? So yeah, so type 1 in one chart is type 1 in any other chart. And pi lower star will give you 0. So that's well defined. And now let's look at type 2. So let's say you have a type 2 in the second chart. And so this, okay, using its chart, the definition is just the integral of GYU, okay, say DU DYI, okay? So in the VU no, what is it? VYU chart. Now, in the other chart, in the oh no, this is V. Yeah, right. So that, now in the other chart, UXT chart, so GYU DU, let's just write DU DYI. So you can express it in terms of the x's, and the DUs, when you transform it to DT, the DTs, you know, you get a determinant. This is a shorthand for, you know, the determinant of the matrix of partial derivatives of the u's with respect to t's. And then over here, you know, you have you have a sum of dyi dxj dxj, right, over j. Okay, so now let me see. So this is, oh yeah, and then GYU is still here. Okay, yeah. So let me see. Is there, no, there's no sum here, right? Yeah, that's right. Yeah. This transforms into this. Okay. And so when you take pi lower star, you integrate this. Yeah. Okay. There's no t's here, so it stays the same. Okay. Okay, now these y's, they're actually, you know, functions of the x's, and u's are functions of the t's, right? So you're integrating with respect to t, and you can use the change of variable formulas by turning this into an integral with respect to u. Okay, and this is still dyi. Now, for this to be true, what has to be true? When you make a change of variables in integration, right, there's a Jacobian determinant, but is that the formula? The formula for change of variables in calculus? Are you shaking your head? I mean, are you saying no? You're saying no. So what is the correct formula in calculus for making a change of variables? Yeah, you need an absolute value here to make a change of variables. And you can put an absolute value there because we are using oriented vector bundles. When you use oriented vector bundles, the fiber coordinates, right, the U's and the T's, they are related by a linear transformation with positive determinant. Okay? And this is the matrix, of partial derivatives. And so by the hypothesis of orientability of E, so, okay, du dt, that's the determinant of dui over dtj. That is positive. And that's why you can put the absolute value sign there. Okay, and that's why you can transform the variables from t to u. All right, and yeah, so because E is oriented, okay, you know that this determinant is positive, and so you can make the change of variables, and you see that when you integrate in the U coordinate chart, the result that you get is the same as the one in the V coordinate chart. Okay, so this is high lower star in the V Y U coordinate chart. Okay. And that proves that integration along the fiber is independent of coordinates, and therefore, if you define it on two coordinate charts on the intersection, they agree. And so, you can define integration along the fiber on the entire vector bundle. That's you define it locally, they agree on the intersections. So, yeah. Oh, yeah, right. Yeah, this is just a number, right? So there's no wedge product. Thank you very much. The next one here. Right, good. If, and then, the next theorem is that high lower star does not commute with D, but there's a sign. Okay. Now, in the book, there's no sign. And that's because the way I write differential forms is different now. So now, I put the space coordinate at the end. In the book, I put the space coordinate in the front. And if you put the space coordinate, dyi, in the front, and you define integration along the fiber, then there's no sign. They commute, okay? Which is better? Is it better to have a sign or not to have a sign? Actually, this is better. I think this is more correct. Okay. See, it's because D has degree 1. And pi lower star, it lowers the degree by r, so it has degree minus r. Okay. D raises the degree by 1. Okay. That means as an operator, this has degree 1. Okay. And pi lower star has degree r. So in mathematics, you know, there is this general rule that when you interchange two things that have degrees, there should be a sign. And that sign should be -1 to the product of the degrees. Okay? And so there actually should be a sign, and it should be minus, okay, pi lower star has degree minus r. So the sign should be -1 to minus r. Okay, but that's the same as -1 to r. Okay. Yes, so this is more correct. The formula in the book is correct, but in some sense it's wrong, okay? Because it doesn't obey this rule. And so now I see that if I put the space coordinate at the end, then I get the formula with the correct sign, okay? All right, so we're gonna stop here today. Yeah, this, you know, you can check yourself, yeah. All right, so I will see you next Tuesday.